Alrighty, good afternoon. Today we will continue our discussion of elimination reactions. We're on lecture supplement. I forgot to write it up on the board. We're on page 13 now. Just to review where we were talking about reactions in which a leaving group and a hydrogen on a beta carbon are removed, and that leads to a new carbon-carbon pi bond. And we talked about one mechanism. We'll talk about another one today, but we talked about one mechanism for this process in which the CH bond is broken by base at the same time the pi bond is formed, at the same time the leaving group leaves, i.e. it's a concerted process. There's a rate expression for that involving one molecule of the thing being eliminated, one molecule of base, and by the way, these reactions, these E2 processes require a strong base. And because the rate law is bimolecular, we call this E2 elimination bimolecular. Now, last time we were talking about how to handle a circumstance in which there is more than one possible product, which alkene product would be the major one. And we talked a little bit about the case where 2-bromobutane can react with strong base, hydroxide, to make a terminal alkene, 1-butene, as well as a pair of internal alkenes, E and Z, 2-butene. So we talk, and this, by the way, is the empirical evidence. The experimental data says that the internal alkenes, together as a group, are formed in greater amount than the terminal alkene, and this is known as Zaitsev's rule, basically. It says that the more substituted alkene is the major product in this kind of process. So we began to rationalize why that was, and said, as a general rule, on the top of page 14, as a general rule that when we're thinking about the ratio of products in a reaction, which one's the major one, we can think about a circumstance in which the major product is the one that's formed simply most quickly. So there's maybe multiple pathways competing. Whichever pathway proceeds most rapidly, lowest energy of activation for its rate determining step, that will produce the major amount of product. That's called kinetic control. But there's also a process where, regardless of the rate at which the products are actually produced, the mechanism allows those products to be in equilibrium, and so then the major product becomes the one which is more thermodynamically stable. That's completely irrelevant to rate of formation, and we call that process thermodynamic control. So we were trying to apply both of those different models to our E2 reaction. Now, first we talked about kinetic control, so the rate of the pathways. And if we're going to talk about the rate of these three different competing pathways, of course we need transition states. Here are transition states that lead to them. And we came to kind of two important conclusions. Number one, the transition states are here written in the order of increasing amount of energy. So increasing bad interactions, as it turns out. The first one has no bad gauche interactions. This one has one bad gauche interaction. That's the bromine and the methyl. And then the transition state leading to the Z alkene has two gauche interactions there. So as we're going down the page, the energy of activation for those processes goes up. The transition states become more expensive, and consequently, that should be the order of decreasing amount produced. This process predicts 1-butene is major, and then the 2-butenes are produced in less. There's another aspect to this particular transition state, and that is, even though a transition state is the highest energy point along a mechanism step, Mother Nature doesn't pick the pathway that's the absolute highest energy possibility of the different transition states that are possible. She still wants to take the lowest energy one, wants things to be as low energy as possible. It's like, here's a metaphor I thought of yesterday. Let's see if it works. How many of you have ever had to move, say, out of your dorm room into an apartment? Right? Okay, so the rest of you, how many of you have ever moved in your life? Okay, so that'll work. When you're moving from point A to point B, now there's a transition state there. You got to pack up all your junk. You got to drag it down the stairs. Convince your friends to help you, right? Rate limiting step. Definitely convincing your friends to help you. So you want to move, and you have to expend energy to do it, but you don't make it the hardest way possible. Of course, you go and ask your friends. You don't say, no, I've got 5,000 friends on Facebook, but, I don't need to ask them. I'll do it all by myself. I will take the refrigerator down the stairs and up the stairs all by myself. Of course not. You don't do it the hardest way. You have to move, so you have to do the transition state of actually moving, but you try to make it as easy as possible. Same thing with the reaction, right? So these transition states, while they are higher energy than the reactants or the products, are the lowest energy pathway that's possible to get there. And part of the reason that they're lower energy for the lowest energy possible is because the atoms are arranged in a way that maximizes the bonding. And here, since we're losing a carbon-leaving group bond and a carbon-hydrogen bond, but gaining a pi bond, that gaining a pi bond has a particular geometrical requirement. The CH bond and the C leaving group bonds, those are becoming the p orbitals that are going to overlap to make the pi bond. And you want those p orbitals to overlap in the transition state, so as soon as the pi bond is beginning to form, you can have that. And that requires that the carbon-hydrogen bond being broken and the carbon-leaving group bond being broken, it requires that those bonds lie in the same plane, so that as the p orbitals grow in, the p orbitals can be parallel to each other and make the pi bond. This is what we call the periplanar requirement for this. Periplanar means they lie in the same plane. Most of the time it's anti-periplanar. Those groups want to be on the opposite sides from each other, so that minimizes the energy. We can have them periplanar if they're eclipsed. That would be called syn-periplanar, but that's more energy. So this E2 process has that the periplanar, most of the time anti-periplanar, but the periplanar requirement in its transition state. Now, if we take what we've concluded here about the rates of these three mechanism steps and how that would influence the amount of product formed, we said that 1-butene should be formed in the greatest amount because its transition state has the least amount of torsional strain. Then comes E2-butene followed by Z2-butene. Well, the problem with that is that doesn't agree with the prediction. As a matter of fact, it's exactly opposite. The prediction was that the experimental evidence was that 1-butene, in fact, was formed in the least amount. So maybe there's another issue here. Maybe the stability of the products has something to do with this. Okay, let's look at that. Let's look at the case, the explanation number 2, where the more stable product is the major one. So we have to look at the alkene stability. Now, we don't necessarily have to make a thermodynamic argument with this. There can still be a kinetic control argument. It's kind of semantics, really, which one you want to use here. But the reason it might also be a kinetic argument, a transition state energy argument, is because that transition states, if we go back and look what we have on the previous slide here, these transition states have some alkene character to them. The alkene is beginning to form. And if the alkenes that we're beginning to make have different stabilities, that's going to influence the energy of the transition state. It's like if you are moving into that new apartment, the amount of energy you have to expend to get into that new apartment depends upon how big the stairs are. All right, remember that refrigerator we were talking about? If the new apartment is down in the basement and it's a ramp, sure, I'll take the refrigerator, that's easy. But if it's like 4 floors up, and there's no elevator, and they're narrow, windy stairs, I lived in an apartment like that once. And when I lived in Philadelphia, it was unpleasant to move in, let's put it that way. Moving out was actually easy. Most of the stuff we had was junk. I lived when I was a college student. Most of the stuff we had was junk. So when we were ready to move out, we simply went down to the first floor, took the communal dumpster, rolled it under our back door by the kitchen, and just kind of pitched stuff off the balcony. True story. As a matter of fact, we had this one really awful couch that we were going to get rid of. Right? So we roll the dumpster over, take this couch out to the kitchen, heave it off the back balcony. It falls 4 stories. And if you've ever thrown out a couch 4 stories and managed to land it right on the edge, you can very hear the couch break. But it didn't land in the dumpster. So we went down to put it in the dumpster, and by the time we walked down 4 flights of stairs and went around the back of the building, the couch was gone. So by the time we walked back upstairs, the couch was back. I think somebody decided that they really didn't like the broken couch after all. All right. So alkene stability matters because it can influence the energy of the transition state. But we're also interested in alkene stability because it can influence a whole slew of other things as well. So let's talk about the kinds of things that influence alkene stability. There are 3 things we're going to talk about. Number 1, strain. Now this, by the way, should say torsional strain, or excuse me, steric strain, not torsional strain, so it's correct. I'm sorry, I used to say torsional, and it means steric. So the difference between those, remember, is strain is, of course, energy that's caused by unfavorable geometry. Steric strain is when that energy, in principle, cannot be reduced by rotating around a bond, whereas torsional is when it can be, in principle, relieved by rotating around a bond. All right, so steric strained and alkene, because we're talking about the groups around the carbon-carbon double bond which can't rotate. Let's do a very simple case, cis and trans-2-butene. There's the structure of the molecules, and you might be able to see some strain issues with those, but it's easier with these representations, but it's actually a little bit easier to see it with these space-filling models. Space-filling models are representations of the molecule where instead of using these skinny sticks, we use the so-called van der Waals radii of the atoms. That's essentially where the electron clouds are. It gives a better indication of how close things are together. So here's cis-2-butene. Here's a methyl group. So here's a carbon of a methyl group. Here's a carbon of a methyl group. And they come fairly close together. As a matter of fact, these methyl groups are so close together that if I wanted to rotate around this carbon-carbon bond, the other one would have to move simultaneously. They're like gears, like teeth on gears. In the trans-2-butene case, here's a methyl and here's a hydrogen, and they're not quite as close together. So what happens to strain when you bring groups closer together? More strain, right? There's more repulsion. Imagine if we go back to our park bench metaphor that we've used several times. If the people sitting on the park bench are even closer together, there's more crowding, there's more uncomfortableness. So here, between the two of these, the cis-2-butene has more strain because it is the two larger groups together on the same side. So trans-alkene more stable than cis-alkene in this particular case. Now, almost every quarter somebody says, you're not making a complete analysis because you're comparing stuff on one face, methyl-methyl, versus methyl-hydrogen. There's stuff on the other face. Don't we have to count that as well? Over here is hydrogen-hydrogen interaction. That's not as strong as methyl-methyl. But in the trans case, we have methyl-hydrogen. So really the difference becomes, in the cis case, one big interaction, two methyls, one little interaction, two hydrogens. Sum those up and you get strain. And then in the trans-2-butene case, we have an interaction which is less than less than methyl-methyl. It's methyl-hydrogen, but we have more of them. We have two methyl hydrogens. So in other words, in the cis case, we have one big and one little, and in the trans case, we have two middles, which wins out. Well, it turns out as the groups become bigger, it's not a linear effect. It's more like not quite an exponential effect. But when you make groups bigger, the effect becomes much, much bigger. So this two methyls is worse. Two methyls plus two hydrogens is worse than two times methyl plus hydrogen. The net effect is it's the methyl-methyl that dominates, and the cis is less stable than the trans. Now, in general, if you look at a whole bunch of other alkenes, that's going to be generally the case. Cis-alkenes are less stable than trans because of that kind of interaction. Now, some students will go to the next step and say, oh, okay, that must mean that E then must be more stable than Z. Because after all, cis-2-butene is the Z2-butene and trans is the E. So if cis is more stable than trans, then, if cis is less stable than trans, then Z must also be less stable than E. That's not true. Because cis and trans and E and Z are based on different things. Cis and trans are based on whether the carbon chain changes position, whether it just kind of flips to the other side, or whether it does a U-turn when it goes through the alkene, when it goes through the double bond. Here's the U-turn. Here's the other side. But E and Z are based on Kahn-Ingold-Prelog priorities. And Z is not always cis. So there's no general relationship between E and Z and stability. All right, so that's one thing. Now, another thing that might matter, or another thing that does matter, is the position of the carbon-carbon double bond in the chain. As it turns out, and this is just a general empirical observation for which I don't really have a good explanation, the alkene would prefer to be internal as opposed to terminal. Now here they have the same number of substituents, the same number of different kinds of bonds and so forth, but as it turns out, terminal is just less favored. And again, I don't have a real good answer for that. All right, another thing to look at is the number of carbon groups attached to the carbon-carbon double bond. Now, as it turns out, having more carbons directly attached to the alkene makes for more stability. And the reason, if you'd like to go through, there's a little discussion here about the bond strengths. You're welcome to go through and see how that works. But basically what it boils down to is it is better to have sp2 carbon to sp3 carbon bonds than it is to have sp2 carbon to hydrogen bonds. So having more alkene to other carbon bonds is simply better, more stable. So more substituents, more things on the alkene makes it more stable. Now, if we put these three ideas together, cis versus trans, terminal versus internal, and degree of substitution, we can write a general trend for alkene stability that we have in the box here near the bottom of page 16. It says that the least substituted alkene, that's ethylene, which also happens to be by default terminal and has no degree of substitution whatsoever, that's the least happy alkene you can get. It doesn't mean it's unstable, it just means compared to other alkenes, it's not the best choice. If I put one substituent on it, so one R group replacing one of the hydrogens with a carbon group, that's mono-substituted, that's a little bit better, but it has no choice of internal versus terminal. If there's only one substituent, if there's a CH2 in the end, it has to be terminal. If I have di-substituted, then I have a choice of di-substituted terminal or di-substituted internal. And as we saw from the top of the page, internal is more stable than terminal. And then tri-substituted is 3 substituents, so we no longer have to worry about terminal anymore. And then all the way up to tetra-substituted, with 4 substituents being the best choice. Now, if you're thinking a little bit about this and kind of analyzing as we're going on, you might say, wait a minute, that seems inconsistent. Because we said on the previous page, where we talked about cis and trans, having alkyl groups on the same side causes a decrease in stability due to torsional strain. And tetra-substituted has to have a pair of alkyl groups on both sides. In other words, adding substituents causes more strain. So why are we saying it's more stable? Doesn't having a higher degree of substitution cause more strain? And the answer is yes, but Mother Nature's preference is that the degree of substitution carries more weight than the strain as long as the strain isn't really awful. So you can put 4 methyl groups on there, no problem. 4 ethyl groups, no problem. It's when the groups start getting really big, then you get into a problem. Down on the bottom of the page, we have kind of a classic example of that. The molecule we have down here is tetra-tert-butyl-ethylene. I know that's a kind of a trivial name. If you like IUPAC names, knock yourself out on that one. It is a tetra-substituted alkene. So there's our carbon-carbon double bond with 1, 2, 3, 4 tertiary butyl groups on there. Right? So that's an example of tetra-substituted. But having tertiary butyl groups next to each other is not good. They're big. This is like putting 4 sumo wrestlers on the park bench. Right? Sumos. Of course, they're going to throw salt on the park bench first, but if anybody here know about sumo? Any sumo fans in here? No? So nobody could ever answer to me why they put down salt, but they don't put pepper or oregano or anything like that. Go look it up on Wikipedia or YouTube or wherever. All right, so these tertiary butyl groups are large. Here, 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 here. They're running into each other, very severely running into each other. They create so much strain. This molecule is so unhappy that it's unstable. Nobody has ever synthesized this thing. People have tried. There's about a dozen different reports of people trying to make it, but nobody's ever actually made it. And I'll give you a way to think about that. We're going to do a little model here. This is an alkene. Whether you believe it or not, this is an alkene. So this is the sigma bond. This is half of the pi bond, so there's another half down here. I just don't have thumbs sticking in that direction. And these are the things attached to the sp2 carbon, so the alkyl groups. In this case, they would be tertiary butyl groups. Now, these tertiary butyl groups are very large. They really get in each other's space. So what do groups do when they get into each other's space? They try to rotate away. So what's going to happen is they're going to try to do this. They're going to try to push away from each other. But what happens to the p orbitals when the tertiary butyl groups push away from each other? The p orbitals aren't lined up anymore, so you lose your pi bond. What happens when you throw away the pi bond? What happens to energy? It goes up. You're throwing the pi portion of a carbon-carbon double bond is worth about 60 kilocalories. And while there's a little tiny bit of flexibility there, if you get more than a few degrees of where they're not overlapped anymore, if they're a few degrees off, then you really throw away a lot of the pi bond. And so because this thing has so much repulsion between the tertiary butyl groups, the repulsion between the tertiary butyl groups is greater than the stability gained from having the pi bond. So the molecule says, I'm just not going to have a pi bond, and it's like this. So you end up having two unpaired electrons on the carbons, and as we're going to see later on in this course, unpaired electrons are unhappy. They want to bond to other things. So that molecule is very reactive. All right, so our general rule is that that increasing degree of substitution helps unless the strain becomes really severe. Now, at what point does the strain become really severe? That's kind of a judgment call. Methyl groups, ethyl groups, okay. A lot of tertiary butyl groups, not so good. There's a gray area in between that you just kind of have to make an educated guess on a case-by-case basis. Now, if we use the degree of substitution general stability trend, what does this predict about what the major products of the E2 reaction are? If the alkene stability is what is controlling the process, then here's our prediction. The terminal monosubstituted alkene. So terminal because the alkene's on the end of the chain, and monosubstituted because the carbon-carbon double bond only has one alkyl group on it. That should be less stable than the internal disubstituted alkenes, and in fact, that's what we see. Remember, it was 19% terminal and 81% of the mixture of the internal. And then even then, we would predict there would be more E than there would be Z. And so, in fact, that agrees. And so that's the explanation we'll use in this case. We'll say that E2 reactions are controlled by the stability of the product. Now, that's kind of a long, convoluted argument we went through to get to that point. But part of the reason I did that is because this idea of product stability controlling a reaction turns out to be very common. So not only for E2 reactions, but for almost every single reaction we encounter, we can predict that the major product most of the time is going to be the most stable one. Now, you might be saying, does that mean thermodynamic control always operates? No. What it means is thermodynamic control operates sometimes, and other times kinetic control has a lot of thermodynamic control kind of aspects in it because of the structure of the product being reflected in the structure of the transition state. So, in other words, we're going to use a general rule that in most cases, not all times, this prediction always doesn't work, but it's a good place to start. If you've got a reaction, I'm mixing A and B, I'm going to make X and Y, and I have to decide whether X or Y is the major one. I'll pick whichever one of those two products is more stable. That's your best guess. This rule also does not apply just to reaction products. It applies to products of individual mechanism steps. So, for example, if I have a reaction that could make a mechanism step that could make two different carbocations, one tertiary and one primary, which one am I going to predict is the major one? Tertiary, because it's more stable. Because the transition state that makes tertiary is more stable than the transition state that makes primary. So a general overall rule. Now, the exceptions to this generally come when there is some structural requirement within the mechanism that overrides the stability issue. In E2 reactions, the main issue that we have to worry about is this periplanarity issue. Remember, the beta hydrogen and the carbon leaving group bond have to line up. They can line up anti, that's by far the most common, but they can also line up syn occasionally. So if the molecule that's undergoing the elimination can adopt any geometry at once, so there's 360-degree rotation about every bond, then it's not an issue. But if you can't get to every geometry, then perhaps some geometries that might lead to E2 are forbidden because we can't get the things to line up. Here's an example. We take this molecule and we do E2 elimination, so we're going to use potassium methoxide strong base. We would say, all right, so where are the beta hydrogens? There is one here, and there are two there. So in principle, we could get two alkenes. We could get one where the hydrogens from the 6 o'clock position are removed, so the new alkene is between 6 o'clock and 4 o'clock. That's what's shown here. Or we could get the alkene where the hydrogens are removed from the 2 o'clock position, and that puts the alkene vertically here between the 2 o'clock position and the 4 o'clock position. That's not shown here. Well, the difference would be trisubstituted internal, that's formed from removing these guys, versus removing the 2 o'clock hydrogens leads to di-substituted internal, which is preferred, which is more stable. Tri-substituted internal or di-substituted internal? Tri-substituted. So that's what we see here. As it turns out, if you change the stereochemistry of the methyl group, once again there are beta hydrogens here and here. But the only alkene we get, actually this isn't even major, this is only alkene we get, is the alkene, the less stable alkene. Where is that coming from? That comes from the fact, and I encourage you to look at a model to see that, that comes from the fact that this hydrogen right here cannot become periplanar with the leaving group. It has to do with the chair conformations available in the 6-membered ring. There are practice problems in the textbook that get you to go to look at that, but I really encourage you to look at the models and see why that is. This is a common phenomenon with 6-membered rings. Now, all right, so there's our general rule. We've just said that. Now, what we've seen here is going to lead us into our next idea, exceptions to Zaitsev's rule. This is an exception to Zaitsev's rule. Zaitsev's rule said elimination gives you the most substituted alkene. Well, here it gave the less substituted alkene. There are some other exceptions to Zaitsev's rule that we run into occasionally that are worth talking about. And when Zaitsev's rule is violated, when the elimination gives the less substituted alkene, we call that Hofmann's rule, named after some guy, Smith. No? All right. There's a lot of things in organic chemistry that are named after people. Even the SN2 reaction is named after a Russian, but nobody calls it that name anymore because there's so many variations of it. I mean, you'll hear about, remember we talked about Chi-Chi bobbin before? That's another one of these name reactions. All right. So there are 2 exceptions to Hofmann's rule that we should, to Zaitsev's rule that we should look out for. I mean, here's one we talked about. We're going to talk about two different ones. Number one, the less substituted alkene can be major when the base that does the deprotonating is sterically hindered. Now, let me give you a metaphor to think about where this comes from before we actually explore this case. Imagine you are coming to class. You're going to drive to class, and it's 2 minutes before 1 o'clock, and it's Chem 14D. You want to sit front and center because these are the best seats. Not the cheap seats in the back. These are the best seats. Studies have shown if you sit up here, you get higher grades. It's a joke, okay? Just because you're sitting here isn't a guarantee. No, you want to come to class. You want to get the best seat. So you're in the parking garage, and you're going, oh my gosh, I have to get to class in 2 minutes. That means you want to pick the very first parking space you can find so you can get to class quickly. Now, of course, if you're trying to find a parking space at 2 minutes to 1, you know that parking garage basically has, if you're lucky, 2 parking spaces available. Let's suppose for this metaphor it does. There's 1 parking space on the 2nd floor, and there's 1 parking space on the, what's the top floor, the 832nd or something? 6th floor, 8th floor, whatever, whichever structure you're in. Now, of course, you want the parking space on the bottom level because it's closer to class. You don't have to run down all those stairs. If you're driving a little car, then like a little smart car, right? The ones you have to wind up with the rubber bands, the little smart cars. Well, around here, I guess we power them with squirrels, but you can go to any parking space you want. Because your little smart car fits in any parking space. So it does not matter if that parking space on the 2nd floor is between 2 Hummers. You can still fit in there, no problem. So little car can go anywhere you want. Now imagine same scenario, 2 minutes to class, except instead of driving a little smart car, you're driving a limousine. Good choice. So you're driving this limousine. Of course, you're driving fast because you want to get to class in time. You come to that space on the 2nd floor, which is between the 2 Hummers, and you've got a limousine. Are you getting in there? I don't think so. Even though that's the more desirable space because it gets you closer to class, you go, gosh darn it, I can't take that one. So you circle around, circle around, circle around, and finally, up on the top floor, you find a space where you can put your limousine. So there, the space you park in is controlled not by getting the best space, but simply where you can fit. Okay? Everybody follow that. Parking space controlled by, you want to get the best parking space, but controlled by what your vehicle is. How does that relate to this? This is you parking. That's the vehicle you're parking is the base. And the hydrogens that you're going to take when you're a base are the parking space. These hydrogens can have different amount of steric hindrance depending upon what's around them. Hydrogens on the end of the molecule, say these methyl groups over here, tend to be less hindered. There's not as much alkyl group stuff around them. The hydrogen here on the CH2, more sterically hindered because it's got a methyl on one side and the rest of the molecule on the other. So when the base comes in, the base says, all right, there's a couple of things. I want to take a hydrogen away and make an alkene. And based, if you'll pardon the pun, based upon what we just learned in the previous slide, you want to take away the hydrogen that leads to the more substituted alkene. But that means taking away the more sterically hindered hydrogen, right? This hydrogen leads to more substituted alkene, but more sterically hindered. So if you're a little base, you can go to any hydrogen you want, and then you get to pick the hydrogen which makes you happiest, the hydrogen that leads to the more substituted alkene. But if you're a big base, if you're driving the limo, then it's hard to get to these more hindered hydrogens. You have to go to the less hindered hydrogens, and then it's simply a choice of you don't get to really choose which alkene you make. There's only one kind of accessible hydrogen. So what it boils down to is, the bigger the base is, the less internal alkene you get, the more terminal alkene you get because of that steric hindrance and base size issue we just talked about. All right, so how does it work? If the base is ethoxide, CH3CH2O-, relatively small base, all things considered, it has a choice, so it's going to make the more substituted, the more stable alkene, the internal alkene more than the terminal alkene. In this case, Zaitsev's rule is followed. But when the base is more hindered, tertiary butoxide, so the O- has got this big alkyl group around it, then it is more difficult for it to get into the more hindered hydrogens, so it takes the less hindered hydrogens more frequently, and we end up with the less substituted alkene as the major one. In other words, Hofmann orientation. Hofmann's rule is followed in that case. So bigger base, more towards Hofmann. At what point does the base become so big that we shift away from Zaitsev to Hofmann? And the answer is, well, there can be an infinite number of bases, of course. But the only base you're going to routinely see that gives you Hofmann routinely is this guy, is tertiary butoxide. All the other bases that we're going to use, hydroxide, methoxide, ethoxide, that sort of thing, we're going to assume that they're small enough to give you Zaitsev as the major one. So in terms of base size, everything does Zaitsev except for terp-butoxide. So that's one thing. Now it also turns out, on the next page, that there is a leaving group influence as well. There are three different groups of leaving groups that in E2 tend to favor Hofmann, tend to favor the less substituted alkene. And that's the case when the leaving group is an amine, a thioether, or F-. Now, I'm going to X F- off because in terms of E2 reactions, you can force F- to leave, but you really, really, really have to beat on it. And it just doesn't work very well. It's very impractical. So for the same reasons that we don't think about F- as being a leaving group in SN1 or SN2 reactions, also not a leaving group in elimination reactions. So it's there because if it does eliminate, it tends to give Hofmann, but it's such an impractical, unimportant process, we're not going to worry about it. So what about these other two guys? When NR3 is a leaving group or SR2 is a leaving group, they tend to give more Hofmann product. Now the reason for that is simply the steric hindrance, the torsional strain that's in the conformation where the different beta hydrogens would be removed. So again, I will leave this to you as an exercise to explore, but consider for this guy down here, compare it with the bromide case, look at the conformations of the molecule that would allow a beta hydrogen to be removed. Is it worse or better in terms of energy when you're lined up with one of the methyl hydrogens or one of the other beta hydrogens? But when these guys are the leaving groups, we tend to get Hofmann. So for example, if bromine is the leaving group, here we have potassium ethoxide. We follow Zaitsev's rule in that the more substituted alkene mixture, right, the internal alkenes are formed to the tune of 69%, and the terminal alkene formed 31%. So that follows Zaitsev's rule. But when the amine is the leaving group, this large amine is a leaving group, now we get almost exclusively terminal alkene and almost no internal alkene that would be a Hoffman case. All right, now we're going to finish E2 here by talking about two other things. Number one, up to this point, every single E2 reaction that we have talked about has led to an alkene, a carbon-carbon double bond. But in fact, it doesn't always have to lead to an alkene. You can make an alkyne, and here's an example of that. If I have a molecule with two bromines and I react it with a strong base, in this case we're using NH2-, that's the conjugate base of ammonia, very strong base. So that can do the elimination to make so we take away, right, here's a beta hydrogens here and here. Take away a beta hydrogen, make the alkene with the bromine on it. You might say, wait a minute, bromine's a leaving group. I still have strong base hanging around. Can I still do E2? Is there another hydrogen which is beta to the leaving group and periplanar? And the answer is absolutely, the other vinyl hydrogen. So that can also be eliminated to make an alkyne. This turns out to be a fairly common way to make alkynes, by eliminating two halogens at the same time. We can also use this in this case to make a carbonyl. Here we have an oxygen-chlorine bond we're breaking, but we're still taking away a hydrogen right here. And in this case, we end up using a weaker base principally because an oxygen-chlorine bond is pretty weak. It's pretty easy to take away. So I encourage you to draw the curved arrows for those, see how it meets all of the requirements in terms of the beta, periplanar, and so forth. Last thing we're going to talk about with E2 is our E2 checklist. Like we have with SN2 and SN1, we could create a checklist saying, here are the kinds of things that we need to have this reaction proceed at a reasonable rate. And I guarantee we don't do this for every single reaction, but it's easy enough to do with E2, so we will. When we're talking about making this reaction occur quickly enough, we're talking about having the rate-determining transition state being relatively low in energy. So here's our transition state, and we might think about the things that are involved. The base, the periplanarity of the carbon-hydrogen, carbon-leaving group bonds, and the nature of the leaving group. So those are the things we look at. We have to have a strong base. Most of the time it's an alkoxide base, RO-, hydroxide, methoxide, and so forth. The protonated version, not good enough. So in other words, we might use CH3O- as the base, but not CH3OH. I bring up that point because many times when we use CH3O-, methanol, CH3OH, is frequently the solvent. So it's the O-, not the O neutral, the O- that's doing the deprotonating. We also need a leaving group. Must be moderate or better. Does that sound familiar? SN2, what was the leaving group requirement? Moderate or better. SN1, what was the leaving group requirement? Moderate or better. What do you think we're going to say through the rest of the course? For this reaction to occur, if there is a leaving group, the leaving group has to be, it's got to be reasonably good, right? Lousy leaving groups don't leave except in specialized circumstances, and we'll discuss those when we get to them. Now, molecular geometry. The carbon leaving group bond and the beta CH bond that we're taking away have to be periplanar. Note that it does not say anti-periplanar. They don't have to be pointing in opposite directions. They can be eclipsed, but they have to lie in the same plane. It's just that the anti-periplanar is just more common. One last reminder about this, since this issue comes up frequently. Because we're using the base like CH3O- in the alcohol that corresponds to, so CH3O- and CH3OH, some people will say, hey, doesn't CH3OH reduce the basicity of CH3O- through hydrogen bonding in the same way that it would reduce the nucleophilicity? And the answer is absolutely true, good observation, pat yourself on the back. Or pat your friend on the back, or on the discussion board say, good observation, or whatever it is. It is true that hydrogen bonding decreases basicity for exactly the same reason that hydrogen bonding decreases nucleophilicity. But as it turns out, the decrease in basicity is not so much that it shuts down an E2 reaction. So we can still use CH3O- and CH3OH for an E2 reaction. Still works just fine. All right. Now, we're going to shift gears slightly on elimination. Still talk about elimination, but do a different mechanism. You may at this point have begun to notice some parallels between E2 and SN2. One of the major differences is that it's both X something providing electrons. If that X something provides electrons to a carbon and it does a substitution, we call that SN2. If that X something provides electrons to a hydrogen and a pi bond is formed, we call that E2. but they both involve leaving groups, and in many cases, strong bases and strong nucleophiles, they can do both. So you might say, is there then a parallel between SN1? Is there a carbocation version of the elimination mechanism? And the answer is, yes, there is. Let's talk about that. Let's think about that by considering this case. Let us imagine that you have 1-methyl-cyclohexanol, and for some reason you want to take away a molecule of water, you want to dehydrate it. I don't know, maybe you're doing an experiment in the chem lab. This is a dehydration that we do a lot in these kind of things. So we take away a molecule of water, and you're going, okay, the OH is going away, we're making a pi bond. Sounds like an elimination reaction. So you go and look at what you learned about E2. In E2, we use a base to take the hydrogen pi bond form, leaving group leaves. Hey, that looks pretty good. We get the alkene, we get the conjugate acid of the base, we put the proton on, and hydroxide goes away. So you go into the lab and do it, and Mother Nature just sits there and looks at you and says, what do you mean? I'm not going to eliminate this. Are you crazy? Go back and look at your lecture supplement. It doesn't work. Why doesn't this work? Now, we're not specifying what the base is. We can assume the base is anything we like. It's not the issue of the base here. It's the issue of something else. What is it that doesn't look so good here? It looks like a good E2 mechanism, right? We have all the curved arrows drawn correctly. Assuming the base, we can make that as strong, as weak as we like. That's not the issue. We're leaving something that we haven't talked about here. What am I leaving out of the conversation, right? We've discussed the base. Make it as strong or as... What am I leaving out? Thank you. The leaving group. Leaving out? I know, it's the middle of the week. For how many of you, the middle of the week is the toughest part? Right? You just want to take your weekly nap all afternoon. All right. I believe me, I appreciate that. How do we think about hydroxide as a leaving group? Doesn't. Boo, that's a good description for it. As a leaving group, it sucks. It only leaves under certain specialized circumstances, and I'm here to tell you this is not one of them. So that's why it fails. All right? We'd still like to do this dehydration, so how can we get around that? Simply throwing in a really strong base doesn't help the lousy leaving group leave. Even though the nature of the leaving group and the base strength are somewhat interdependent, the better the leaving group is, the weaker base we can get away with. But too strong a base, and then you start deprotonating the OH. So that doesn't work. So maybe I can do something to the OH to make it a better leaving group. Why is HO minus a lousy leaving group? Small size of oxygen. I can't do anything about that because I've got oxygen that's going to be the part of the leaving group. So I can't sprinkle magical fairy dust on oxygen and make it into a bigger atom. Right, it's leaving it's attached as a neutral group and it becomes negative as it leaves. That's something I can do about. The reason it's becoming negative, see how it starts as neutral, it's picking up a pair of electrons as it leaves. When it leaves, it's still going to pick up electrons. That's what leaving groups do. But we can deal with the charge. It's picking up a pair of electrons. Its charge is becoming more negative as it leaves. But I'd like for it to leave as neutral. So what does it have to be so that when it leaves, it becomes neutral? It has to start as positive. Positive plus a pair of electrons makes neutral. So I would like oxygen to be positive. How can I make oxygen positive? There's a common trick we use in organic chemistry. Drop a proton on it. So if I put a proton on the oxygen, now I convert the leaving group from hydroxide, bad leaving group, to water, okay leaving group. And how do I do that? Acid. That's what protonates does. So you're actually going to see this trick fairly commonly. There's a lot of times we protonate oxygen to make, and sometimes nitrogen, but mostly with oxygen, to make it into a better leaving group. All right, so here's what we're going to do. We're going to take our alcohol, and instead of reacting it with strong base, we're going to add strong acid. Usually we use aqueous H2SO4. And as a reminder, when you see a strong acid such as H2SO4 or HCl or HBr or HI or any strong acid in water, it's not strong acid anymore. It's H3O+. So when you read aqueous H2SO4, think H3O+. So you could write that either way. So how is our mechanism going to go? We have that in the middle of the page here. Take our alcohol, protonate it with a strong acid. All right? Now we might say, aha, we've got a much better leaving group, so let's do E2. Right? We've made the better leaving group. But You'll notice it says no E2 because. Let's finish that sentence. What are the E2 requirements? Go back to the previous page. E2 requirements. Molecular geometry, I can get any geometry out. Well, it's a cyclohexane, so I've got some limitations. But it turns out in this case, no problem getting up periplanar beta hydrogen. Play with the model and test that. Leaving group? Leaving group's water. That's okay. It's not the best, but it's okay. Strong base. Well, why not? I mean, can't I just throw in hydroxide here? Didn't I ask someone before about giving me $1,000 or $20 or whatever it was? I ask for different amounts every quarter. I don't have hydroxide present. You can't use it if you don't have it. And there's a real obvious reason why you don't have hydroxide in this case, outside the fact that it's not drawn or not generated. If you look at this reaction, you'd go, of course I don't have hydroxide, because this is strong acid and hydroxide is strong base. And what happens when you mix strong acid and strong base? You do a Chem 14Bl titration. Remember those? Yeah. Yesterday you did one. Yeah. I'm sorry to hear that. Have you written your report yet? No? Did you at least write down your data neatly in your notebook? Good for you. All right. Not on a paper towel. No. Okay. So we can't do an E2 here because there's no strong acid. There's no strong, I almost said strong acid. There's strong acid present, but that's irrelevant to E2. There's no strong base present. I don't have it. I can't use it. So what do? Well, it is a tertiary carbon, and it's an okay leaving group, so let's just have it leave. Metaphor. Here's a way to think about it. Imagine you have a fight with your significant other. So you have the fight in the morning, you feel really bad. Well, after you've left, you feel really bad. Probably at the time you don't. You leave, you feel really bad, you come home, and you're thinking, how can I make it up to him or her? So you're thinking about this, you're thinking, roses and a nice dinner. Yeah, that'll do it. I've been mean to them for years, and so I can buy them off with food and plants. So you're walking up to the door with a big bunch of roses, and you've made reservations at someplace expensive. And you'll notice as you walk up to the door that there's luggage sitting outside the door that has your name on it. Right? Last time you traveled and went through LAX, you didn't tear off the tag, it still has your name on it. That's your roommate saying, I've packed your bags, which is an indication that they want you to leave, especially when you discover your key doesn't work anymore. And I'm not saying this from personal experience, of course, but so what we've done here is by protonating the water or protonating the OH, we're kind of packing its bags. We're saying, we protonated you for a reason, we want you to leave. Okay, so let's have it leave. Tertiary carbocation. Not too bad. Moderate leaving group. Okay. This isn't like iodide or triflate leaving to give me a tertiary carbocation with lots of resonance, but it's still okay. So we get a carbocation. And every time you get a carbocation in a reaction mechanism, regardless of where it comes from, here it comes from ionization of a carbon leaving group bond, what do you think about? Three-phase. Now, all of them could be operating. Capture a nucleophile, lose a proton, rearrange. But since we're talking about elimination, let's think about the fates that get me to where we need to go, which is a new alkene. So that would be take away a proton, be deprotonated. We're going to use the strongest base that's present, which is water. It's not a great base, but carbocations, certainly can be deprotonated with water. So I can take a proton off of up here. Either two of the protons at the 2 o'clock position or the 6 o'clock position lead to exactly the same alkene, which is this guy. It is a tri-substituted internal alkene. It has 1, 2, 3 alkyl groups attached to it. Don't think of the ring as a single alkyl group. Doesn't matter that it's a ring. It's the number of carbon-carbon bonds that matter. On the other hand, I can take the proton away from the methyl group, and that leads to another alkene, which is disubstituted and internal. Which one of these two is the major one? Whenever you have a choice between two different reaction pathways, the one that gives the blank is the major one. More stable. So which is more stable? Trisubstituted internal or disubstituted terminal? Trisubstituted internal, that's the major one. Now, there's like one more page to go with this, but so I don't want to rush it. We'll finish that up on Friday. So you might want to just look at our last page, our E1 requirements, and we'll start from there on Friday.